Hello team. In this video we're going to talk about full virtualization, which is the most commonly used virtualization approach in data centers today. And this is because full virtualization provides many properties that we want. First, full virtualization provides transparency. So to a tenant, a virtual machine is just like the real hardware. They can run whatever operating systems they want. They can run these operating systems unmodified, and on top of these operating systems, they can run whatever application they want. Full virtualization also provides isolation, which means that one virtual machine cannot impact another. For example, if a virtual machine uses a lot of resources, the other virtual machines should not get slower. And isolation also means that a virtual machine cannot take control of the hardware, so they cannot read memory that is used by other virtual machines, and they cannot, for example, encrypt the hard drive so that the server can't run any other tasks. And finally, full virtualization provides very high efficiency. So it virtualizes resources with low overhead and close to native performance. And the previous approaches we've discussed up to this point do not provide all of these three properties. For example, emulation has very high overhead and performance is very low because each emulated instruction takes many instructions in the native architecture to complete. And paravirtualization, similarly, also doesn't satisfy transparency because the operating systems need to be modified. So if you have an operating system that you cannot modify, say Windows, then you can't use paravirtualization. So how does full virtualization achieve all of these goals? Well, full virtualization requires changes to the hardware so that we can achieve all of those goals. So I said before that Intel CPUs and many other CPUs, they have multiple privilege levels. So user applications run with less privileges than the kernel. So the kernel, because it has more privileges, can control what applications do with the CPU, with the memory, and with input-output devices. Now, because we want to run applications and operating systems unmodified, we want to keep the same infrastructure unchanged. So what they did was to extend processes so that they have additional privilege levels, and so that the hypervisor actually runs below the kernel with more privileges than the kernel, and then we can apply the same ideas. So the applications will run in ring 3 with the least amount of privileges. And the applications are controlled by the guest operating system, which still runs in ring 0, unmodified. So the guest operating system has some privileges over the hardware and it can manage applications, but it doesn't have complete control over the hardware. The hypervisor runs in rank -1, so it has more privileges than the operating system, and the operating systems, like the guest operating systems, are managed by the hypervisor. So the hypervisor controls the guest operating systems just like the guest operating system controls the applications. In full virtualization, the hypervisor mediates access to the hardware, and this has several similarities with how operating systems mediate application access to the hardware. So the hypervisor allocates CPU to a virtual machine, and the virtual machine can run until its kernel needs to perform a privileged operation. When the virtual machine needs to run a privileged operation, the hypervisor will take control and check that the virtual machine has permission to do that operation, and if it does, then the hypervisor will take care of doing that operation on behalf of the virtual machine. And the hypervisor can also preempt the virtual machine if it doesn't release the CPU. So the hypervisor starts running a virtual machine on the CPU. If this virtual machine doesn't leave the CPU, if it doesn't, for example, perform a privileged operation, the hypervisor will preempt the virtual machine, will kick the virtual machine out of the CPU and take back control. And then, same thing the operating systems did before. If the hypervisor sees that there's a virtual machine that uses too much CPU, it can adjust how much CPU it gives to that virtual machine in the future. The hypervisor also allocates memory to a virtual machine. So virtual machines run on virtual memory, and the translation of virtual addresses used by virtual machines to physical addresses on the actual hardware is ultimately controlled by the hypervisor. And finally, the hypervisor mediates a virtual machine's access to input-output devices, like we're going to see in a future video. So this is the figure we've seen before when explaining how the operating system schedules the CPU across different processes. And this is the same figure explaining how the hypervisor schedules the CPU between different VMs. So we can make a parallel. So when VM0 is running, it keeps running until it needs to perform a privileged operation or when its times run out. And then the control passes on to the hypervisor, and then the hypervisor will save state of the virtual machine. And then the hypervisor can, perform any tasks that it wants, like allocate memory to virtual machines, take care of input and output, and then it might decide to run a different virtual machine, like VM1. So it will reload the state of VM1 on the CPU, and then VM1 will run until its, CPU allocation expires, or it needs to perform a privileged operation. So the same thing that we had for applications, we're going to have now at a different layer for virtual machines. And of course, when VM1 is running in ring 0, it will pass control of the CPU to applications that will run in ring 3. So this is not drawn here, but VMs will run applications inside them. And this is the same slide that we used to explain how the operating system controls memory use by applications. So an application uses virtual addresses, and the virtual addresses are translated to physical addresses by the memory management unit that resides within the CPU, and the memory management unit is controlled by the operating system. Now, when we run in full virtualization, we have an additional layer that is controlled by the hypervisor. So virtual machines, for example, running Windows as their guest OS, will operate on virtual memory. So they will have virtual addresses. And these virtual addresses will be translated to machine virtual addresses by the memory management unit. And these machine virtual addresses will be translated into actual physical addresses that we will use to address the memory by nested page tables, which are also inside the CPU. So the memory management unit is managed by the guest operating system. And these nested page tables are controlled by the hypervisor. So the hypervisor has ultimate control of which physical address will be accessed by the guest virtual machines. And the fact that the memory management unit is managed by the guest OS means that the guest OS has some control of the hardware, so it can allocate memory to its applications and achieve high performance, because these changes within the guest operating system doesn't need to go through the hypervisor. But the hypervisor can still manage the memory because it controls the nested page tables. And whenever the guest operating system needs to change the nested page tables, then the hypervisor will take control and verify that that change is permitted. So here's a comparison among the virtualization approaches we've discussed. So for emulation, the main idea is to emulate instructions from one computer architecture on top of another architecture. Emulation can run any software given you have the emulator, and it doesn't require anything from the hardware, and it provides full isolation. So it's great on these properties, but the main problem with emulation is that it's very slow because of the high overhead incurred in emulation. For paravirtualization, we've seen that the main idea is to modify guest operating systems so that they can run unprivileged in ring 3. Paravirtualization has high performance because code runs native most of the time, and the only overhead we incur is when we need to call the hypervisor to perform privileged operations. The main problem with paravirtualization is that we need to modify the operating systems, so we can't run any operating system that we want unless we can modify the operating system. And paravirtualization has no requirement on hardware and isolation, so these two are okay. And finally, we've seen that in full virtualization, the idea is to run the hypervisor with more privileges than the guest OS, so that the hypervisor can control the guest OS. And full virtualization has great performance, so the guest operating system and the guest applications will run at native speed because the hardware has support for full virtualization. The software can run unmodified, so that's great, but we do need hardware changes to support full virtualization. So old CPUs from Intel and AMD didn't have virtualization support, but most modern versions of processors do. And again, full virtualization also provides complete isolation. So isolation is provided by all techniques.